So today in class, I reintroduced solutions to you guys. I realize that we've been working with the concept of solutions since the fall term, but we're going to take it to a different level. So tonight in this screencast, I'm going to discuss three ways in which we can measure the concentration of a solution. One of them is something you're familiar with, which is the molarity. The second one, which is a little different, is called molality. And then the third is called mole fractions. Now, something I just want to reiterate, which I might have talked about in class today, although since I'm doing this screencast on the Saturday before the class that we have on Monday, who knows what I got to in class. But the concept of concentration is a very important one because I want you to be clear in your mind that it's a fixed ratio that you'll always have with regard to determining the concentration of a solution. So for example, if we were to take a look at this larger box that you see out here, this larger cube containing whatever it is that dissolved particle is right there, that has a particular concentration. It looks like, all right, I just counted it. There are 30 of those little dots in a particular volume. So let's imagine that volume is a full liter. And then if you want to scoop out just a smaller volume of that, a portion of it, you wouldn't have the same number of ions. Obviously, you'd have a smaller number of those ions floating around, but the ratio would be the same. So it would still be the same 30-to-1 ratio, even if you don't have a full liter. And the same thing can be said even for this smaller volume right here. Of course, you're going to have a smaller overall amount, but the ratio of the solute to the solvent is not going to change. So in that way, it's important for you to know that the concentration of a solution isn't going to change depending on the amount of that solution you're working with. However, the number of moles in that amount certainly will change. Number of moles of both things, the solute and the solvent. Now, molarity, which is something that you are already familiar with, which is moles of solute divided by the number of liters of solution. The one thing I want to be sure that you do understand when we measure this concentration with molarity is that to this point we really haven't taken into account the volume associated with the solute, which is the stuff that we're actually dissolving into the solvent. But in reality, you really should. Molarity always takes that into account. Now, for the most part, you're adding such a small amount of the solute that it really doesn't make a difference in terms of the overall volume of the solution. But if you're doing it correctly, if you're in the lab and you're a chemist who's actually preparing a 3.0 molar solution of something, then you do have to make sure that you take the volume that's taken up by the dissolved solid into account when you're doing this. And so in this drawing here, or in this set of photographs, it's kind of cool to see. Here you can see that we have a little bit of the solvent, which is in this case, let's say it's water, and then we have some amount of the solute that's up there. We go ahead and we dump the solute into the solution, into the water, and it dissolves just like that. It completely is going to dissolve as long as there's enough solvent there to dissolve it. And then the third step here is you're going to fill the rest up to a very specific mark. So this is called a volumetric flask, and there is this line etched into the glass that is exactly 1,000 milliliters or 1 liter of solution. And so if you fill up the water to that point, then you know that you're going to have an exact whatever molarity. I said it before was what, 3 molar solution. You'll have an exact 3 molar solution, which does take into account the very small amount of volume that's taken up by the solid after it dissolved into the water. Okay, now you see here I've drawn a schematic showing the Atlantic Ocean between the US and the Spain, so you're looking northward here. And the reason I bring this up is because we need to talk about one of the problems that you have when you start talking about concentration and you use volume when you're dealing with liquids. Now, we all understand that with global climate change, that the air around us, the atmosphere, is increasing in temp. The problem with that is that through convection and through conduction, that's also going to increase the temperature of the Atlantic Ocean. And you all, I know, have understood, because it's in the popular press these days, that as a result of the ocean increasing even slightly in its temperature, that causes the ocean to expand. And of course, if you're going to expand into the same volume, which is essentially what you have here, that means you're going to actually raise the sea level here. And so maybe the Statue of Liberty has its toes in water in the next century or so as a result of global climate change. The reason that happens is you have this thermal expansion is because don't forget that this water consists of a whole bunch of molecules. And if you give them kinetic energy, then they're going to be moving around faster. And if they're moving around faster and bumping up against each other and then the sides of the container, which is in this case the ocean floor, it's going to, because of that excess kinetic energy, the entire mass of water is going to expand. Just like you can imagine if you had a balloon and you put it into a very warm room, that balloon is also going to expand because of the kinetic energy associated with the gas that's inside that balloon. So if we go back to this situation that I pointed out to you folks earlier, we might have a problem if we're doing this in a room where there's actually a high temperature. Now, when you're dealing with volumes that are this low, 1 liter, it's not really going to make that much of a difference. But I want you to imagine that theoretically it is going to make a difference, because 1 liter of water at room temperature is going to be very different than 1 liter of water at, say, 30 degrees Celsius, which is around 98 degrees. Okay, and so if you have to then deal with the thermal expansion of water, it seems like there's probably going to be a better way. There should be a better way to measure concentration that doesn't deal with something that changes according to the temperature. And that's where we bring into the story the concept of molality. Now, actually, just in case, let's scooch down here. It's not a bad idea for me to put molarity as moles of the solute divided by the number of liters of the entire solution. Okay, we've all understood that, and we know that it's also sort of that funny italic M that we use. And again, liters of solution is a bad thing if the solution is obviously it's a liquid, and if it's a liquid and it can expand according to the temperature, it's gonna mess up our calculations of molarity. So with molality, we're looking at something a little bit different. Moles of solute over kilograms of solvent. Now, the important thing about kilograms is that that's not going to change. You can heat up a kilogram of water, and it's not going to change the mass of the water in even the slightest amount, unless you heat it up so much that you have boiling and so you're losing some of that water. But if we assume that we're not losing any of the water, heating it or cooling it is not going to change the mass of the solvent. And notice too that we're not taking into account in this situation the mass associated with the solute. It's only the mass of the solvent and just the solvent alone. Oh, another thing I wanted to point out is that the symbol, as we know, the symbol for the molarity is this capital script N. Well, the symbol for molality is a lowercase m. It's a little confusing because we also use a lowercase m for mass, but I promise you we're not going to have calculations that have both mass and molality as variables. I'm always going to give it to you in kilograms, and so you'll see it as kilograms or grams or something like that. All right, so let's imagine a problem here. What is the molality of a solution containing 450 grams of water and 62 grams of sugar, C6H12O6? So the first thing you need to do is a mole conversion to convert the 62 grams of sugar into moles. And when you do this, you generate 0.344 moles of the C6H12O6. Whoops, I don't think I was recording there. Sorry about that. So what I did here is I took the 0.045 kilograms of water and I put that in here as the denominator. I took the 0.344 moles of C6H12O6, put it in my numerator, and came out with 0.76. Okay, so now the last way to measure the amount of a solute in a solvent is through a process called calculating the mole fraction. And this is actually a pretty straightforward situation here, so it's not going to be too complex. I'm going to explain it to you with a problem. Okay, so here's the question. If I have a solution containing 2 moles of ethanol, and in this case ethanol, since it's the smaller amount, despite the fact that it's a liquid, is going to be the solute, and 8 moles of water, the solvent, what is the mole fraction of the ethanol? Now, it's a piece of cake here, because all you do with the mole fraction is create a fraction, and that is the fraction of the solute, whatever you're looking at. In this case, it's the 2 moles of the ethanol, ETOH, and you want to put that over the total number of moles of solution that you have. So the total number of moles of solution is going to be 2 moles plus 8 moles, or 10 moles of solution. And when you chuck that into the calculator, you get a number of 0.2. No units associated with this because the moles cancel each other out, but that is the fraction of the, in terms of moles, the fraction of ethanol in this entire solution that contains ethanol and water. Okay, so lastly, I have a slightly more difficult question because I haven't converted these things into moles for you. But what if I was asking for the mole fraction of 12.3 grams of C4H4O in 1 gram of C2H6O? Now, it's worth pointing out that this material here is called furan, and this is ethanol. So these things are both liquids in this case. And so the first thing you need to do, obviously, is figure out the number of moles of furan and the number of moles of ethanol that you have here. By the way, I just made a quick change here. I meant to write 100 grams of ethanol, so it's down here as 100 grams. Anyway, the answer here is that you're going to have, 0.181 moles of the furan, and you're going to have 2.17 moles of the ethanol. So if you were to do the mole fraction here, you'd take that 0.181 moles of furan divided by the total number of moles of both furan and the ethanol together, which is 2.35 moles. Throw that to your calculator, you get 0.0770 for your mole fraction of the furan in this solution. Okay, bye.